So hi everyone, today I'm going to introduce my final project for the advanced machine learning classes. My topic is video classification. So video classification, it's a process of categorizing video content into different genres and themes based on visual and auditory information. This involves analyzing sequences of frames to identify patterns and features that can be used to determine the video's content, such as sport, movies, and new clips. In this project, I am investigating the application of two specific machine learning models, convolution network, aka CNN, and the combination with recurrent network, aka RNN, and transformer model to classify videos. The project's focus is to assess how efficiently these models recognize and categorize video content. Considering their unique approaches to processing temporal sequences and spatial features within the videos, the goal is to identify which model performs better or for video classification tasks. Before diving into the model architecture building, we will introduce the dataset that we're using to train our model. The specific model set, the dataset that we are picking is the UCF-101 dataset. It is a comprehensive collection of realistic action video, primarily sourced from YouTube, and it's widely recognized for its use in human action recognition research. This dataset includes more than 13,000 video clips distributed across 101 action categories. These categories encompass the diverse range of human activities, such as sport, musical instrument playing, and various types of human interactions. The total length of the video clips is spent over 27 hours, offering a rich and varied source of data for analysis. And the specific reason that we pick on this dataset is that it covers a wide spectrum of human actions and provide a robust platform for training and testing videos classification models across a variety of scenarios. And out of 101 action categories, we choose five specific categories. That is ghost streaming, playing video, playing pianos, typing, skiing, and fencing. The reason we focus on similar action, choosing playing pianos and typing, is due to their visual similarity in hand movement, posing a challenge for the model to accurately distinguish between the two. So next, we're going to dive into the combination of CNN and RNN model and the architecture. In the actual building here, we have four layers. We have the first layer, it's the mobile net architecture. This is a key component selected for its efficiency, which is paramount when dealing with the high volume of data present in the video frame. This efficiency does not come at the most accuracy, but it make it ideal choice for real-time application. And as you can see in the actual code there, I comment out another model for the CNN base, which is VGG16. The reason we did not pick that because it's a huge model and it assesses my GPU memory usage. So instead, I choose with mobile net, which is also a good alternative. The second layer is we flatten the reading thing that we gain from the first base layer. And then we have the LSTM model, which in turn of long short-term memory network with its 128 units is tuned to capture the temporal aspect of video data. Besides, the strategy comprise to ensure detailed temporal analysis without overburdening the computational load. And finally, the model employs a softmax output layer. This is the industry standard method for classification tasks as it provides the probabilistic output across multiple classes, which in our case corresponds to 5 categories of action we have to classify. This helps ensure that the model's prediction are both interpretable and actionable. And for here, you can see the summary of the model that we built. Just a short picture showing you each layer and how much parameter in each layer we are able to train. So for your next model, we have the transformer models. And in this specific model, this is a state of art of the cloud architecture to have a game changer. So we definitely want to have to try on this model and set apart of its self attention mechanism, which intelligently assess to the relevance of different part of the input data. In our case, video frame. So in a transformer model, we have specific four layer also. And the first layer is the positional embedded layer. It's to imbue the model with a sense of order of frame in the video. The transformer encoder with self-attention for capturing complex long-range dependency across the frames. Um, um, and the global average polling and then softmax layer for class prediction. And here we have the result for our first model. Um, as we can see at the graph, the model converged relatively quickly, demonstrating both high training and validation accuracy with minimal and overfitting observed. The training loss indicate consistent improvement in accuracy and decrease in loss over 14 epochs, showcasing the model learning efficiency. And one thing that worth mention is that originally the plan is to focus on 30 epochs, but we enable feature something called early stop whenever and the patient with 5 epochs, whenever in 5 epochs we not seeing any further improvement within the training, we will stop the training process and return the best model within the training process. So that's why we only see 14 epochs. Instead, I set the original default epoch to 30. And in the case here, we could see it could be pretty clear to predict the action in the video. And I didn't make a GIF video out of the frames. So instead of showing the 5 frames here, and the model can correctly predict the class is belong to the seeking class, which is correct. Here we have the result from our transformer model. The transformer model, while achieving reasonable accuracy, faced challenge in terms of the computational efficiency and resource utilization. Um, as you can see in the prediction class here, the resolution it's relatively low. That's because when I want to train the model, I want to originally use the 128 times 128 resolution, but due to its high memory usage, I have to coast down to 32 times 32 times 3, this low resolution. This resolution downgrade impact the clarity of video frames, potentially affecting the model's trainings and performance. And the model also require a longer training duration, uh, which you can see in the picture there. The converge observed around 130 epochs. This intended training period coupled with considering resource consumption highlight the model's complexity and computational demands. But at the end, I'm pretty happy that the accuracy of the model can reach nearly at around 100%. So let's do a comparative analysis based on this two model. We could see as we see the two graph, the accuracy and the loss based on the epochs, we could clearly say that the combination of convolution neural network and the recurrent neural network model outperform the transformer models in terms of accuracy, achieving high level of classification accuracy more rapidly. In terms of computation efficiency, their combination of CNN and RNN model was more computationally efficient, converging faster and requiring fewer resources compared to the transformer model, which struggle with memory constraints and require a lower real solution for feasibility. The challenge, as we have said about earlier, the primary challenge for the transformer model was managing its memory usage and training time. And in the contrast, we also facing some other challenging when we're using the combination of CNN and RNN model, because it's benefit from a pre-trained model, which is the mobile net that we talk about. It leads to a smoother and more efficient training process. So in the future, we would probably employ a more powerful GPU and memory use to train the transformer model in case we could better compare the actual result and prediction ability to the CNN and RNN model. And thanks for listening to my presentation for my fellow project, and that's to the end. Thanks for your time.